now. So, good morning everyone, and welcome to the Center for Theoretical and Computational Physics weekly seminar. Today, it is a pleasure to welcome Catherine Barentin from the University of Lyon, one in France. So, Catherine did her PhD at the University of Strasbourg. Then this was followed by postdoctoral appointments at UCLA in the US and the University of Bordeaux in France, after which she joined the University of Lyon, where she now is. And today she's kindly agreed to tell us about her work on wetting of yield stress fluids. Before I hand over to Catherine for the truly interesting stuff, just a couple of announcements from me. First, this seminar is being recorded, so by staying on, you're giving consent to your voice and image being recorded and stored. Second announcement is, in the interests of internet stability, can I ask everyone, except the speaker, of course, to mute their microphone and switch off their camera during the seminar. If you wish to ask a question, then of course you're free to unmute yourself and switch on your camera if you so desire. So without further ado, it's over to Catherine for the seminar.
Oh, thank you, Paolo, for the introduction and for the invitation. It would be a bigger pleasure to be with you in Lisbon, but it's like that. So next time I will come in your lab. And so today I will talk about some experimental results on wetting properties of yield stress fluids. So I do all my research in a group named Surface and Interface at the Institute of Light and Matter. And our main research deals with soft matter, wetting properties, hydrodynamic of simple and complex fluids, and experiments goes from nanofluidics to macroscopic scale. So it's really a big group. So now I will introduce my subject. I hope I have a pointer. No, not yet. I will add a pointer. We did that. So you can see it, yeah?
Yes, we can see it now.
Okay, nice. So I will start with the introduction, and I will present first what is a yield stress fluid. So yield stress fluids are complex fluids whose property depends on the applied stress. So as we can see on these pictures, a yield stress fluid can behave like a liquid if the stress we apply is higher, a critical one, and it behaves like a solid, elastic solid if the stress is below a certain critical stress we call yield stress. So this intermediate behavior between solid and liquid is really interesting for many applications in food, in cosmetic, in buildings, but make their understanding more complex. So one important thing is that if the internal stress are below the yield stress, like maybe at the bottom here, the stress cannot relax and do not relax, and this will be really important for my talk. In our everyday life, we have many yield stress fluids around us. We can think of emulsion, polymeric gel, or foam. They seem to be very different. In fact, not, because what they share in common is their structure. All the systems are concentrated suspension of soft particles. So in case of emulsion, the soft deformable particles are the droplet of oils in water. In polymeric gel, the soft particles are what we call microgels. It's a small elastic ball. And in foam, the soft particles are bubbles of air surrounding by soft films. And all these systems share in common also their mechanical response. If you apply a certain shear rate, you make it flow, you want to make it flow. First of all, the yield stress fluid will respond like an elastic. Then it will deform plastically, and then finally it will flow. So depending on the solicitation, you can see a yield stress fluid like an elastic, like a plastic, or like a fluid. It depends on the solicitation. So if we make it flow, we can, do you see all my screen? It's okay, because I have my face on the screen. So
no, we can see all of it. There's a plot on the left and then an equation on the right.
Okay, so no problem. So if we want to measure the relation between the stress and the shear rate, we measure what we call a flow curve. And for a yield stress fluid, we obtain this kind of data. At low shear rate, the stress reach a plateau, which gives you the yield stress. And below this value, there's no flow. And above it, it will flow. And the flow curves is well described by an empirical law called Herschel-Berkeley law that links the stress applied to the system, the yield stress, and the viscous dissipation and the shear rate is at the power n, and n usually is smaller than 1, and in the experimental system, it's often close to 0.5. So it's a non-linear relation between the stress and the shear rate. Okay, what are my motivation to study weighting of such complex systems? In fact, many applications involve interfaces and yield stress fluids, so it's a practical motivation. So we can think of coating experiments like on this strawberry, spreading like here, 3D printing, or imbibition porous media. In all that case, you have many interfaces and you have complex fluid. There's also a fundamental motivation. In fact, weighting has been mostly studied with Newtonian and simple fluids for a long time ago. But simple fluids are characterized by an internal stress which relax. And for this system, we can develop energetic arguments. Okay. So when we talk about weighting, an important, crucial parameter is the surface tension. Just a short definition. So surface tension is the energy per unit area needed to create an interface. And we can define it thermodynamically or mechanically. It's the derivative of free energy with respect to the area at constant temperature and volume. And mechanically, it can be seen as the force per unit length that tends to decrease the area of the interface. And for simple fluids, for Newtonian fluids, both definitions are equivalent. But as we will see, it's not so obvious with yield stress fluids. Finally, we say that we have a weighting situation when we have free media in contact, like a solid or liquid, a vapor. And in that case, we have free interfaces and so free surface tension. I will always denote it big gamma, the liquid vapor surface tension. And in partial weighting situation, we have what we call a triple lane and a contact angle. And this contact angle for simple fluids is set by the value of a free surface tension and is well described what we call the Young's law or Young-Dupree's law, depending on the country where you are. So it's the introduction. And so now we want to study complex situation, complex weighting. So you have two choices. You can have a simple liquids on soft surfaces, It's a complex situation because this weighting will induce a deformation of the soft surface, and many groups study that, and don't talk about that. The situation I will consider is always a complex fluid on a solid surfaces which is not deformable. Okay. So now I will, if I have time, do not hesitate to interrupt me. I will talk about 3 experiments. And with these 3 experiments, I will ask the question, what is the influence of a yield stress on the law? And comparing, and we will compare always with the case of simple liquids. The first experiment I will show you is capillarized. So, and I will ask the question, what is the influence of a yield stress on the Green's law? We know with simple liquids. The second experiment, we develop a setup to measure the adhesion between 2 surfaces induces by a liquid pitch, and with this experiment, we were able to measure the surface tension of Yieldstress fluid. And finally, if I have time, I will talk about spreading of a drop made of Yieldstress fluid. So, the fluid I use is a commercial one named Carbopol. So, Carbopol is a suspension in water of polymer microgels. So a microgels, as scheme here, is an elastic ball made of cross-linked polymers. And for Carbopol, the polymer is a polyacrylic acid. In such system, the microgel size is typically around 1 and 10 micron. And if we change the concentration of the polymer, we can change the property of the yield stress fluid and change, for example, the yield stress value. But as you can see, we put only a really few quantity of polymer because they swell a lot in water. Finally, I use also a suspension in water of linear polyacrylic acid. It's the same chemistry, but there's no crosslink, and so the rheology is different. There's no yield stress. So we have systems with a chemistry really close, but with a rheology which is really different. Okay. So now, capillarize. So this work has been performed during the PhD of Baudouin-Géraud in collaboration with Laure Petit and Pierre Job. And so the experimental setup is indeed quite simple. The most difficult thing is to have really clean surfaces and capillaries. So we have a reservoir of Carbopol, of Yieldstress fluid, and we have glass slides forming a capillary. So when we approach the Carbopol from reservoir from the glass slides, and when the Carbopol touch the plates, the capillary starts, and we can follow the capillary thanks to a fast camera. So we use 2 kinds of geometry. We use glass plates with constant gap, separated by a constant gap, or we use a glass plate forming a corner. This geometry is nice because we can study in one experiment the influence of a gap size on the capillaries. Okay, so I use such geometry instead of commercial capillary because it's really easy to clean them. We just have to open the system, put it in an ozone plasma, and then it's really clean. And we can also control the roughness of the plate. If we want to make them rough, we can sandblast them. Okay, so now the result. In fact, what I did is the experiments performed by Taylor really long time ago. He did it with simple liquids in a corner geometry, as you can see here. On the left part, the two glass plates touch them, so the gap is close to 0. And on the right, there's a certain gap of 1 millimeter. So here are the results. So I remind you, on the left part, the glass plates touch them. And on the right part, the gap is around 1.4 millimeters. So we have a certain range of gap size. In black, you see the result of the capillary rise with a simple fluid. It's exactly the experiments performed by Taylor, and they say, oh, we see the hyperbolic shape due to the Drin's law that tells you that the height increase inversely proportional to the gap size. Okay. In blue, I show you the result with a yield stress fluid characterized by a yield stress of 4 Pascal, and in green, with a yield stress of 10 Pascal. So, main observation. First of all, higher is the yield stress, lower is the capillary rise. Second thing, higher is the yield stress, lower is the dependence with the gap size too. And finally, the yield stress prevents from the divergence at 0 gap. There's no divergence anymore at 0 gap. So, are the main observation. The second observation we did is that the roughness of the plates plays the roughness of the plates play a huge role. In contrary with what happens with simple liquids. And here I show you the result of a capillary rise between 2 smooth plates and with a capillary rise between 2 rough plates. You see, in smooth plate, in smooth condition, it rise, the same gel rise much higher than in rough condition. So how to explain all that result? So to modelize and to understand the maximum height reached by the yield stress fluid, what I did, in fact, I solved the dynamics and I solved the Stokes equation. I didn't take the inertial terms into account because I was interested by the end of the capillary rise, so when it's really quasi-static. So I solved the Stokes equation and I integrated it over the gap size. And when we do so, we obtain a force balance, which tells you that the capillary force is the driving force and the preventing force are gravity and the stress exerted, the viscous stress exerted by the wall onto the liquids. So, and this is true for any kinds of fluids. So we have a link between the height at any time with the stress at the wall at any time. Okay, so if I have a simple fluids, what can I say? If I have a simple fluid, when the capillary rise stops, the shear rate goes down to 0 and the viscous stress goes down to 0 too. So we find that the maximum height by a simple liquid is just described by the Drin's law we know, which is that the H is inversely proportional to the gap size. And this we can find it by minimizing the energy. That means it's a thermodynamical equilibrium. So what happened with yield stress fluids? When the capillary rise stops, in fact, the stress at the wall doesn't go to 0. It tends to the yield stress. So that means there are internal stress that do not relax. So it's a dynamical arrest, and the maximum height we can expect is the one where we fix the stress at the wall to the yield stress. So it's our expectation. So it's a modified Drin's law that takes into account the yield stress. So now we want to test this prediction. So we use one of our experiments, and we fit, knowing the gap size, we fit the experimental data with the law we suggest. And we have two unknown parameters, the capillary force per unit of length and the yield stress. So by fitting the data, we obtain value for the yield stress. And in fact, the value we obtain by fitting the data is in really good agreement with the value that the reometer gives us independently. So a good news is that looking at the capillaries gives us information about the value of the yield stress. Okay. So now, how to understand what happens in smooth condition? I remind you, we obtain capillaries higher than in rough condition. To understand that, we measure the flow curves with a reometer using different plate geometry, smooth planes and rough planes. So the purple curve is obtained with rough planes, and the blue curve is obtained with smooth planes. So as you can see, at high shear rate, the two curves coincide, but at low shear rate, which corresponds to the end of the capillaries, you see that the stress measured in smooth condition is much lower than in rough condition. So how to interpret that things? In fact, it's the signature of slippage. In yield stress fluids are known to slip along smooth surface due to the existence of a small lubricating layer along the smooth plate. So the stress is lower just because it's easier to make the system move as it slips. So if we consider that the stress at the wall is smaller than the yield stress, we understand that a smaller stress at the wall induces a higher increase and higher capillary rise. So what we say is that slippage, the reason why the height is higher in smooth condition is due to the boundary condition is due to slippage. So a summary, we extend the Green's law, and we say that the maximum height reached by a yield stress fluid is not an equilibrium, thermodynamical equilibrium, it just corresponds to a dynamical rest. Slippage plays an important role. And finally, I didn't have time, but if we study the dynamics of a capillary, we can measure also biological parameter like the exponent M. So with experiment, I explore, in fact, viscous properties and plastic properties of yield stress fluids. So now I didn't say, we didn't know another parameter that was the surface tension of Carbopol gel. We didn't know what value to use in this expression. We just fit the experimental data. So we look at the literature and see what we could find. And in fact, in the literature, we find different values for the surface tension. So the fact that there's no consensus on the value of surface tension tells us that maybe measuring surface tension of yield stress fluid is not so easy. So we decide to investigate that things, how to measure surface tension of yield stress fluids. So to do so, we measure the adhesion force between two surfaces induced by a liquid bridge. Don't worry with this ellipsis quite clear. It's just an optical artifact. It's a plain liquid bridge between two plates. So this work has been performed during the PhD of Lorraine Janssen in collaboration with Marie Lemaire and Hélène Delanoë-Ayari. So capillary adhesion, it's the adhesion induced between two surfaces by the existence of a liquid bridge. And there's an adhesion because the pressure inside the liquid is smaller than the pressure outside the liquid. And this is why a wet sandcastle can stand, in fact. So how to measure this adhesion? So here is the experimental setup. We have a small liquid bridge. Typically, the height of the liquid bridge is about 1 millimeter. And it's in between two glass plates. So we have to have a clean glass plates. So the lower glass plate is related to a mobile stage, so we can compress and extend the liquid bridge. And the upper plate is related to a flexible cantilever. And by measuring the deformation of a cantilever, we can measure the force exerted by the liquid bridge on the upper plate. So I will show you a movie of a typical experiments. So we start with a liquid bridge quite compressed. Oh, excuse me, doesn't work. I don't know why.
It's working, yeah, it's working.
Thank you. So we first stretch the liquid bridge, then we compress it, and then we stretch it again, and then we stop the experiments when the evaporation becomes to be important. And we stretch it by step, and each step, in fact, lasts for 1 minute because we wait for the relaxation of the force. And when the force has relaxed, we measure the force and we take an image. Okay, so the system is small, 1 millimeter, so we can expect that capillary will dominate the yield stress. A second important thing is that we can stretch or compress the liquid bridge, and it will give us really crucial information. And last things we perform, as I told you, we make step, we wait for the relaxation of the force. So we do what we call a quasi-static experiment. So we can neglect viscous effect. Okay, so we can exactly calculate the addition if we have a simple liquids. So we can calculate the force exerted by the liquid bridge on the upper plate at the level of the upper plate, but for a technical and optical reason, we decide to measure the capillary force at the neck, because at the neck we could measure really easily the radius and the curvature of the liquid bridge. But if we do so, we need to add to the force the weight of half meniscus. So the force exerted by the liquid bridge on the upper plate has a capillary force and a weighting force, and a force due to gravity. And the capillary force has two terms: the force exerted on the perimeter, okay, and the force due to the difference of pressure, okay. And all this term is proportional to a length, L, we call L, which depends on the radius of the liquid bridge and on the curvature. Okay, so I show you with simple liquids here. I plot the force minus the weight of the half meniscus as a function of L. And we did the experiments with water and with oil. And during the stretching, compression, stretching, all the data collapse on a single curve, which is a straight line. And the slope of a straight line gives you the surface tension. Okay, so we verify our setup with simple liquids. So now what we get with complex fluids, Yieldstress fluids. So here we have a Carbopol with a yield stress of 5 Pascal. So first of all, we stretch the liquid bridge by step, and we measure a straight line with a slope of about 672 millinewton per meter, which could be the surface tension of the liquid bridge. But when we compress the liquid bridge, we got another straight line, but with a smaller slope of about 50 millinewton per meter. So it's what can we say with these two slopes? We don't know yet. If we increase the yield stress, we see that the hysteresis between stretching and compression increases, and that the difference between the two slopes increases. And you can see that we got surface tension during the stretching, which is of the order of 110 millinewton, which is not a real value possible for water with something. It's much higher. So what we measure, it's not a real surface tension, it's an apparent surface tension. And so I draw a scheme to explain you why during the stretching we measure a higher surface tension, during the compression we measure lower surface tension. So during the stretching, what you have to remind you is that you stretch an elastoplastic systems. So the elastoplastic system fights against the stretching. So you have an elastic force that fights the stretching, and the capillary force also tends to attract the two surfaces. During the compression, the capillary force has always the same sign. It tends to attract the two plates. But the elastoplastic force exerted by the Yieldstress fluids fights against the compression. So the sign of the elastoplastic force changes. So during the stretching, we measure a total force, which is a sum over two forces. And during the compression, the force we measure is the difference between two forces. So now we calculate exactly what happens inside the liquid bridge. So we decided to develop what we call an elastoplastic model. And we calculate the internal stress induced by deformation inside the liquid bridge. Okay? And as we wait for relaxation of force, we simplify the response of a Yieldstress fluid. We just consider that it can be an elastic or it can respond plastically. Okay. So now we need to calculate the stress inside the liquid bridge, the internal stress, and calculate the force induced by this internal stress on the upper plate. And we say that the force is a combination of, the total force is a combination of two forces, a capillary force and an elastoplastic force whose sign change when you change the direction of deformation. And we take the following value. Okay, so during the stretching, in fact, the stress inside the liquid bridge first increase and then saturates at the yield stress value. And we got a straight line whose slope is close to 70 millinewton per meter. Then we reverse the direction. So we have first an elastic deformation and then a plastic deformation. And here you can see there's a transition due to elasticity. And then we have the plastic deformation. And we got a second slope, which is smaller, as in the experiments. We play with the value of the yield stress, and we find that if we increase the value of the yield stress, the hysteresis between the two experiments increase also. And what the model tells us is that during the stretching, inside the liquid bridge, the stress saturates at sigma y, and during the compression, the stress saturates at minus sigma y, and that elasticity plays a role only during the when you inverse the deformation. And our model tells us that if you average the two experiments during compression and stretching, you can just obtain the capillary force. So what we say is that to get the surface tension, we just have to average our apparent slope. And we got a value close to 60 millinewton per meter, in fact, which is exactly the same value we've got with the suspension of linear polyacrylic acid without yield stress. So in this experiment, we explore the elastic and plastic behavior of the yield stress. So if there's still time, I can speak about spreading of drop. So Paulo, I didn't look at time.
You're okay for time, yeah.
Yeah, okay. Yeah. So last experiment, we studied drop spreading and drop made of yield stress fluid. So this work has been recently done by during the PhD of Grégoire Martouzet, and has given an article really recently. So we asked the question, in fact, what is the final contact angle when you spread a drop made of yield stress fluid? So the setup is always easy. The most difficult thing is to have really clean surfaces and avoid evaporation. So we have a closed chamber, we have a glass plate, we have a pipette with which we approach really gently a droplet. And we can look, thanks a mirror, to the spreading. And then using a camera, we can take pictures at the end of the spreading, measure the final profile and the final contact angle. And here, because of time, I would just talk about final contact angle. So experiments first, we done it with the system which has no yield stress. The system spreads quite a lot and then stops at a final contact angle, typically of 10 degrees on glass plates. And this angle doesn't depend on the drop size or wool roughness, quite independent of different parameters. When we do the same experiments with Carbopol microgel, you see we obtain really complex shape. We can have really complex shape, really different contact angle. And we see, in fact, that the final contact angle depends on the size of a drop. Here you see you have two pictures. The yield stress is the same, but the size of a drop is different, and we get different final contact angle. And we also see, if we look at those two figures for a same size of drop, the higher is the yield stress, higher is the final contact angle. So with complex fluid, we measure that the final contact angle depends on the yield stress and on the drop size. So here is the proof of what I say, the dependence of the final contact angle as a function of the yield stress value. So we can go from 25 degrees to 75 degrees just by changing the yield stress value. This was done for the same size of drop. And if we look at the influence of the size of a drop, here in green, we have the result with the suspension with no yield stress. So the final contact angle is mostly independent with the size of the drop. And here is the result with yield stress fluid. You see the final contact angle increase with the size of a drop. And this is really contrary to what is obtained with simple liquids. And finally, we see an influence of the roughness. Rough plates, on rough plates, we obtain a higher final contact angle. And the difference is quite huge, 20 degrees between smooth and rough plates. Okay, so to understand all that things, I also solve Stokes' equation, and I assume that the driving force is capillary and that preventing force, preventing force is viscous dissipation. So to calculate that, I balance the power, injected power, and the dissipated power. So to calculate the power injected by capillary force, it's quite easy. you just have to multiply the force, capital force, times the velocity of the triple lane. Okay, and the capital force depends on the distance to the equilibrium. Closer from the equilibrium, smaller will be the capital force. So this is easy to calculate. The viscous dissipation is a little bit more complex. So we have to integrate the viscous dissipation per unit volume on the volume of the drop. Okay. And to do so, I assume that we have a quasi-static flow. I assume that we can use the relation I show you at the beginning of my talk. I impose boundary condition, free interfaces at the liquid air interface. I assume that slip is possible. If I don't want slip, I put Vs equal to 0. And the most important thing, I say that viscous dissipation diverge in the corner. So I can use lubrication approximation. So we solve it numerically, but also I could calculate something by hand. At the end of the spreading, we know that the stress is really close to the yield stress because the drop is about to stop. So everything is close to the yield stress. So I can replace in this integral sigma by sigma y. And if we do so, we find that the viscous dissipation, the viscous power, it depends on the size of the drop, on the yield stress, on the velocity of the contact line minus the slip velocity. And there's a numerical prefactor I cannot calculate just with scaling law. So if I balance the two power, I found that the final contact angle is the equilibrium contact angle, just in case if the yield stress is 0 or if we have a perfect slip. And if we have a partial slip or no slip, and if there's a yield stress, the final contact angle will be always higher than the equilibrium contact angle due to this dynamical arrest. Okay, so we perform experiments on rough plates, so we expect no slip. And with no slip, my asymptotic limit tells that the distance to the equilibrium depends on the size of the drop, on the yield stress, on the surface tension with a certain parameter I don't know yet. And if this has no dimension, it's known as the Bingham capillary number, okay? And if I replot all my experimental data like this, I plot the distance to the equilibrium as a function of the Bingham capillary number, all the data collapse. And in the straight line corresponds to the numerical resolution, and the dotted line corresponds to the asymptotic limit, and with the prefactor alpha equal to 0.5. Okay. And if on smooth plates we expect slip, so to explain experiments in smooth condition, I just have to fix the value of the slip. And I found that using this value, that means a proportion of slip of 60% typically, I can explain the angle I measure on smooth condition. So to conclude, I will say that weighting experiments show and weighting results show that there's a strong importance of internal stress, residual stress. The flow and the deformation history is really important. Boundary condition can play a big role due to slippage. And so what we have to do is always a stress balance instead of energy minimization. And most of what I observed was a dynamical arrest instead of thermodynamic equilibrium. Okay. And with this conclusion, I will stop and I will thank you for your attention. Thank you.
Okay, thanks very much, Catherine, for a very interesting talk indeed. And now it's open for discussion. Who has any questions? Please raise the little hand, blue or yellow, whatever the case might be. Come on, who has a question? Right, well, maybe I can start. Just a question first, a technical one about your capillary bridges. Those capillary bridges you study, they're axisymmetric, right?
Yeah, exactly.
Okay, and what's the contact angle at the plates? It's the same at top and bottom too.
Mostly, and yeah, mostly, but as you can see, we have different kind of liquid bridge here. Most have quite the same angle, but it's not so easy to see really close to the plates. So that's why we decide to measure all the things at the neck. And and an important thing is that due to symmetry, some stresses is zero at the neck, and it was smarter to work at the neck.
Right. Okay. Okay. Very good. Okay. So, questions? Anybody else?
Maybe it was too experimental.
Oh no! Certainly not. Certainly not. Well, I'll ask another question then. It's a more general one concerning these yield stress fluids.
Yeah.
From the pictures you showed, I get the impression that well, when you talk about yield stress fluids, you're mostly talking about tensile stresses. But, well, from solid mechanics, you can also apply compressive stresses, and usually the stress-strain curves or the stress-strain rate curves are not symmetric. What's the case here? What happens here? I mean, do you get the same yield stress if you apply a tensile or a compressive stress? Because compressive stresses are also relevant, say, in the case of foams.
Yeah, I understand. In fact, to measure the yield stress, usually we do not compress or we do not stretch the things. We shear it at constant volume. So we apply always shear things. And there are two ways to measure the yield stress. You apply stress and you just look if it flows or not. It's the best experiment, the more precise. But you have to be patient. Or you do what I did, you apply high shear, and then you decrease slowly the shear rate, and then you tend towards the yield stress.
Yeah.
And the experiments, the normal experiments in compression and stretching can be a little bit difficult because you can have what we call you have to expel water from your medium just to compress, and you have to do things really slowly just to, it's what we say, porous aqueous, I don't remember the name, but compression and stretching could be more difficult for measuring the yield stress. Yeah.
Okay, because I was just wondering whether one might see something similar to the Bauschinger effect that you find in solids.
Yeah.
This asymmetry of yield stress and then strain hardening, that sort of thing.
Yeah. I understand. Yeah. Another thing, if we compare with solid, usually the important term is elasticity, Young modulus and things like that.
Right.
And with yield stress fluid, most of the time is the yield stress the most important because really fast, we have plastic rearrangement. But Jean-François Jany did model for small elastic things with the foam things capillary, and in that case, we make a competition between capillary force and elastic deformation, and for solid. But for a yield stress fluid, it's more a competition between capillary force and yield stress. That means plasticity.
Okay. Right. Any more questions? Well, I have one final question actually concerning these capillary bridges, these nice capillary bridges that you're showing, and you explained the hysteresis in your results for stretching and compressing on the basis of whether the force you have to apply has the same direction or the opposite direction to the force the bridge induces between the two plates. But now imagine, I don't know if this is possible, but imagine that you had a bridge made out of a liquid that actually has a liquid that doesn't wet the plates, whose contact angle with the plates is greater than 90 degrees. Now, what would happen now? Would it be the other way around?
In fact, if you have a liquid bridge that doesn't wet, you won't have an adhesion because the pressure inside the droplet will be higher than outside.
Yeah.
But in fact, we expect that the capillary force will push always the plates. So the capillary force will be of the opposite sign, but always opposite sign. That means the capillary force is attracts or repulse. But the elastoplastic force depends on the direction of the deformation. So I expect the same kind of result. That means hysteresis.
Okay, I see.
Yeah, but you have to push your system if it's a non-wetting situation. Yeah.
Right. Okay.
Yeah. So I thank you for your questions.
Thank you. Right. So, any more questions from the audience? Come on, guys. Don't be shy. This is your chance.
This last chance.
Yes, your very last chance to ask a question before we wrap up.
Yeah.
Well.
So.
Yep. Please go ahead.
People study wetting in your group?
Yeah, actually we had people permanently studying wetting a few years ago, although probably a bit less so now. But I myself am definitely interested in wetting and liquid bridges. You will remember that I talked about liquid bridges at Barcelona. So currently we are interested in a slightly different problem, which is if you have a liquid bridge and you apply a sideways force. So not along the bridge, but perpendicular to it. You done any work on that at all?
No.
Like if you have a bridge that's blocking a channel and you blow on it.
Nice.
Something like that.
Nice.
And looking at this also for different contact angles at the bridge on the plates. Although so far we've only looked at Newtonian fluids, but we have this idea that maybe non-Newtonian and Yieldstress fluids will give some interesting results.
Yeah, but Newtonian fluids, if you have no Yieldstress, for example, I did experiment with viscoelastic systems with no Yieldstress. It's just a question of patience. You have to be more patient because it's more viscous, but most of the time they will reach the equilibrium. But sometimes it's evaporation can be interesting with reo shear thinning or shear thickening systems. So many interesting things.
Okay, very good then. Okay, looks like there are no more questions. So let's please join me in thanking Catherine again. Catherine, thanks very much for your seminar, and we hope to see you again soon sometime.
Yeah, I hope so. Thank you for the invitation.
Okay, thank you.
And So bye-bye.
Bye. So the next seminar in the series, which will be the last one before the summer break, will be in a week's time, Thursday of next week. So thank you all for coming and see you then. Recording stops now.